Good afternoon, everyone. Welcome to the fall semester of the I4 Energy Center seminar series. Sorry, starting this semester, we don't have enough money to pay for lunch, but there are cookies. So instead of feeding your stomachs, we're going to feed your minds with stimulating seminars. And we have a terrific speaker to start off the series today, Dr. Federspiel. He's the founder and president and chief technology officer of Vigilent. Dr. Federspiel, in 2004, building on his pioneering research in dynamic cooling technology and wireless networking to address the emerging need of treating cooling and energy consumption as a managed resource, founded Vigilent. Dr. Federspiel began his career in R&D at Johnson Controls after receiving his bachelor's in mechanical engineering from the California Polytechnic State University in San Luis Obispo and his master's and PhD from MIT. In 1998, he joined UC Berkeley, where he was a specialist at the Center for Environmental Design Research and the Electronics Research Laboratory. And I was fortunate enough to work with Cliff around 2003, 2004. Yep. So let's welcome Cliff.
Thank you, Gaiman. And thanks to all of you for coming. It's good to see some friendly faces in the audience. And welcome to all of you who I don't know yet. So Vigilent is a company that focuses on cooling management in mission-critical facilities. So I thought I'd talk to you about some of the problems, issues, kind of interesting technical challenges there, and give you a little bit of idea of what we do to solve some of those and the results that, that derive from that. So mission-critical cooling. So data centers are a good example of that, although data centers aren't the only type of mission-critical facility. So I'd include in that, and we focus on not just data centers where you have racks of servers and things like that, but also telecom central offices where you have a very similar situation. In either case, you have electronic equipment that produces a lot of heat, and the heat has to get out or bad things happen. And when bad things happen in these kind of facilities, they're really bad. So pointer, Gavin?
I'll be right back.
Yeah, OK. So these are the racks here that have servers and switches and routers and stuff in them. This is one of the cooling units in this particular data center. In this case, that's just a great big box. It's got a cooling coil in it that has cold water piped to it from a central chiller plant. But sometimes these boxes have compressorized cooling in them. And there's other ways to get the heat out of these data centers. But this kind of a scenario with a floor standing box on a raised floor with perforated tiles delivering cooling to racks or bays if it's a telecom office is a very common scenario in these kind of facilities. And so what does it mean when it's mission critical? Well, what most people expect in mission critical is it's just basically virtually always up. And when it isn't up, it's a really big problem. And I'll talk a little bit more about that in a minute. This is typically the most expensive asset that a company owns. Even a small data center costs tens of millions of dollars to build. Big ones are hundreds of millions. That iCloud data center that Apple's building is about $1 billion facility. So that's a really expensive asset, really important, and it has to work. The maintenance costs in these facilities are much higher than in a building like this because the system is never down. So you have to perform maintenance in this very high uptime, mission-critical environment while everything's up, everything's going full production. So the costs of doing that are much higher than they are in an admin-type building. And these buildings consume a lot of energy. Even a small one can have a multi-million-dollar utility bill. And so all those create a lot of challenges for managing and operating these facilities. So just to give you an idea of some scenarios where these are actual cases where things have gone wrong in data centers. So most of these I can't tell you who it was or anything like that, but here's an example, a 6-minute outage due to a chiller plant failure, $14 million in lost revenue and penalties from a 6-minute downtime. Another situation, 15 minutes, $25 million. That's a pretty big penalty. That's a scary thing if you're an operator of one of these facilities. There's a lot of, because of the energy consumption of these data centers, there's a lot of effort these days in building these high-efficiency data centers of the sort that Google, Facebook, and Yahoo are building. A lot of these don't use compressors at all. They bring in outside air to cool, and if they need more cooling, they'll use spray cooling, basically glorified swamp coolers to cool the air and get the heat out. So this is an example of one of these where on a hot day, where it was supposed to be bringing in hot but dry air, the outdoor air dampers closed and the humidifiers went to 100% because they had a bug in their BMS programming. This resulted in condensation forming in the power supplies and servers shutting down spontaneously. Obviously a catastrophic outage for that facility. And so these are kind of like, sort of whole data center failures, but there's also kind of individual air conditioner unit failures that can also result in outages. So here's an example where they had a single air conditioner failure. They had sensors in the data center that would read temperature and signal that out to an alarm message to somebody to let them know it's getting too hot. But because only one of them failed, those are reading about 80 degrees and it didn't trip the alarm. But it did cause the NetApp storage to get exposed to temperatures over 100 degrees Fahrenheit and shut down. Now, these NetApp storage arrays are big, and they're really, really important to the operation of one of these data centers. So even though this is a single air conditioner unit failure, this was like an all hands, everybody who runs that data center was there fixing that problem at 3 o'clock in the morning. And that is just not a fun event if you're running one of these facilities. So if you're an operator, what do you do? Well, what they typically do is, first of all, they buy a lot more cooling than they need. They run all of it all the time, which is basically this policy. This is the way I think of it: always on and always cold. They just want to be basically blowing a lot of air that's freezing cold, so that even if something does fail, it's so cold that by the time it starts to get warming up to a temperature that's uncomfortable for the equipment, they've had time to react to it. And then, a lot of the time, surprisingly, they have fairly limited instrumentation. The example I gave you, there were the sensors in the wrong place. They just didn't invest in enough instrumentation to really catch the small failure that ended up tripping them up. And they know that they don't have this, that they're exposed to these vulnerabilities, so they're going home at night praying that they're not going to get that 3 o'clock in the morning call. So the more capacity than needed. Here's a visual example of that. So this is a state of California data center, and you can see they haven't. This is actually just 180 degrees from that photo I showed you before. They just haven't filled this in yet, and yet they have all these air conditioners. And before we got in there, all of them were running all the time, because in fact, they had tried to manually shut some of these off because they knew they didn't need it. These guys aren't idiots. They know that doesn't need to all be on all the time. But when they did shut them off manually, they'd get a shift in load, something would change, and they'd get an incident at 3 o'clock in the morning. So it's just like, forget it. It's just all on all the time. It's got to be that way. Now, on the energy side, this is the scenario. So this is from a report that was done for the EPA by folks up at Berkeley National Lab. And this shows data center energy consumption in billions of kilowatt hours. So the blue is the server storage, stuff like that. The white is cooling power distribution. And you can see it just escalating, 2000, 2005, 2010. And this has gotten so acute in some parts of the country that, for example, in Northern Virginia, where basically the commercial internet started, the utility there, Dominion Power, 10% of all the electricity that they generate goes to data centers. In the next 5 years, nearly 2/3 of the load growth that they're going to see is going to come from data centers. And the other interesting little statistic I found on the internet is that if the data center industry itself were a country, it'd be the 5th largest consumer of electricity in the world. So this rapid growth and the fact that it's just so big is creating a huge amount of pressure on people to deal with it. So in the US, we have new codes and standards that are changing, that are forcing at least new construction for mission-critical facilities to use less power. Title 24 has provisions that are coming down the pike, as well as ASHRAE Standard 90.1, which ties into DOE federal standards. In other parts of the world, not so much here in the US, but in other parts they have carbon taxes. So some of the Scandinavian countries in the EU, the UK has a carbon tax. Australia is thinking about having a carbon tax. And all these basically just increase the cost of power and drive more pressure to do better. Now, in Japan, they don't have incentives there, you know, the way that they do here. There's no rebates in Japan, and historically anyways, and they don't have carbon taxes. I think they just basically rely on two things. One is the fact that it's really expensive, electricity in Japan, so that alone just sort of drives people to be conservative in their use of electricity. And they have they have sort of a social mindset that, you know, I think causes people to sort of work together to do the right thing. But of course, as all you guys know, they had a massive earthquake and tsunami that took out the Fukushima nuclear plant. And as a result of that, the Japanese people have lost confidence in nuclear power, and they have now all 54 nuclear reactors permanently offline. And that's created a gigantic energy crisis in Japan, where the government is now going to big businesses and saying, you know, we'd really like you to reduce your consumption by 25%. 25%, just like we just want it to go down by 25%, because when the summertime comes around in Japan, it was really hot this summer in Japan. Like, the buildings just they have no air conditioning. They just hand out little fans. You know, you're in a conference in Japan, in a conference room, and everybody's just doing this because it's you know, 85 degrees in the conference rooms because they can't afford to use air conditioning just to keep people comfortable. And so they're making really big efforts to solve that crisis that they have, in particular in big loads like data centers. And so one of the ways that people deal with efficiency in the data center is by design. So I mentioned already a little bit about the Facebook, Google, Yahoo type data centers that they use free cooling. You know, outside air is sometimes cool. In the middle of the night, it's cool outside. I mean, why are you running compressors to make cold air when there's cold air right outside, right? And that kind of thing is working its way into codes and standards. Some of those get rid of the compressors too, the chiller for, you know, the hot summer days, and they use things like spray cooling. And then variable speed, you know, the sort of 10 to 15 years ago kind of data center had no variable speed. Everything is just on, it's running full speed, it's just moving lots of air and lots of cooling fluid. And so variable speed is becoming much more prevalent, and the Japanese are really, really good at this. Because of the earthquake risk in Japan, they don't like having water in their data centers. So they don't want to have big chilled water plants piping water around. They don't want to have spray cooling in their data centers. So they build air conditioners that have compressors in the air conditioners, just like your home air conditioner, except that it's all variable speed. Every component, every motor, the compressor motors, it's all variable speed. And as a result, they're able to deliver, you know, twice the efficiency of conventional types of air conditioning of the same sort that you find in other parts of the world. And so that's what they do for efficiency by design. But that doesn't necessarily get you an efficient data center, because you can destroy that savings by bad operation. Well, I wouldn't say bad, but by having operation practices that waste and interfere with the design that was intended, you know, perhaps to be efficient. So the always on, always cold is clearly not an efficient way to operate your data center. You don't need to have the full capacity of your cooling equipment running if you don't have the full capacity of the load, and most facilities don't. So this sort of works two ways. If you're making a very cold data center, you're transferring heat into, you know, the floor, the walls, the ceiling, all this stuff that's outside the data center. And in a lightly loaded data center, that's a bigger fraction than in a heavily loaded data center. In a heavily loaded data center, you know, there's just so much heat generated inside that little bit of parasitic loss to the outside is kind of negligible. But by being able to raise the temperature of the data center, you can improve the efficiency of the air conditioning equipment. And so having this strategy really destroys the efficiency of the equipment. Designs are usually like a fixed thing at the beginning of time, right? You design your data center. On paper, it looks great. It's got a low PUE, which is an efficiency metric that people talk about for data centers. But then when you start operating it, everything changes, and it's no longer, like it was when they designed it. You have a different load and a different layout and just different things. And all of those changes may mean that the design isn't quite right anymore. The other thing, and this is what I'm going to really focus on more in this talk, is even in these high-efficiency data centers, challenges that really eat up efficiency are the instability of the controls in these facilities. So this is from one of these high-efficiency data centers. This is straight off the internet. They just publish a whole bunch of stuff about what's going on in this one. They have these air handlers that are operating in parallel, delivering air to the same place, strongly interacting with each other, and no surprise, if you know much about controls, they fight with one another. In other words, it's unstable. The normal, almost overwhelming control strategy, though, is just simply return air temperature control of the air conditioners of the sort that I showed you in the photos earlier. So it's like this. So you saw that blue box in the earlier photo. They have a temperature sensor on the top of it that senses the temperature of the air being drawn into. So this is a downflow unit. It draws air from above itself, down through the unit, through these filters, into a cooling coil below that, and then discharges it into the raised floor so it gets dispersed throughout the data center. And that sensor is connected to controls down here. So on this panel, you can set what temperature you wish you could get at this point. And there's just a simple feedback loop. It's a completely decentralized, often not even networked for monitoring purposes, control strategy. And the reason for that is it makes it very easy to just sort of plunk these things down wherever somebody thinks that they need more cooling in the data center, and they don't have to really think about the control operation of the facility. And I showed you some pictures already. You can see that there are many of these, but this is a pretty typical for sort of a mid-sized data center, the scenario. So these are the rows of racks here. And so you can see there are, I don't know, like a dozen of them across here or something like that. These are the air conditioners around the perimeter. So this particular one has 22 of these air conditioners. And they've arranged this in a nice arrangement. So they have cold aisles and hot aisles and cold aisles. So the blue is the cold and the not blue is the hot aisle. And they, literally, they're just right next to each other. And most of these data centers are like those photos I showed you, where it's just completely open plan. Air follows the path of least resistance. And so you end up with strong interaction between these units that, consultants and operators, they observe this, and you see talk at conferences and things like that about fighting behavior and instability. So we've looked at whether or not anybody has done a real technical job at the stability analysis of this kind of a system. And amazingly, we find none of that. I can't find a single paper at a technical conference, from, say, a place like Berkeley or a place like LBNL where they've actually taken a look at this and figured out how it works and why it works the way that it does and what might be better. So we've done a little bit of that ourselves, and I'll just show you what that reveals. So this idea of pairing the return temperature with the chilled water valve or compressor, whatever it is that's the mechanism for cooling in that unit, is a pairing combination that you can use process control techniques that are commonly used for process control, where you want to have decentralized control, but you want to figure out what's the best way to combine a sensor with an actuator. And this tool, this technique called a relative gain array, is something that was developed back in the 1960s by a guy named Bristol to solve just this problem. Which sensor should I pair with which actuator in my process so that I can get the best control? In this case, though, the pairing combinations are set. We don't get a choice. It's already been dictated by the equipment manufacturer. And so the diagonals of this relative gain array are the only thing that really matter in this analysis. Normally, you get this array, and then you make selections about which which input and which output you want to combine together. And the way you interpret this array is that if you get values less than 0 at any of the, in this case, on any of the diagonals, that means the system is going to be unstable in one way or another. If it's 0, it implies that there's no influence of that control on that actuator. If it's 50%, it implies that the interactions are about as strong as the loop feedback for that control loop. If it's 1, it implies that there's no interaction, so this is what you'd like to have, nice and easy to control. And if it's greater than 1, it means that the interactions decrease the loop gain. So as it gets greater and greater and greater, you get a situation where it gradually gets harder and harder for that loop to be controlled. So this is a graphic of that data center that I showed you with the 22 air conditioners. So it's a visual of the relative gain array. And so you can see that this color here, this kind of teal color, is 0. Blues are less than 0. And the diagonal, like I said, is what matters. And so here you can see we have less than 0 there. We have some close to zeros here and here. And if you look at the numerical values, what we see is the minimum diagonal is less than 0. It's minus 0.3. We have 4 of them that are less than 0.5. And the result is that this system with return air control is unstable. You can just look at it, if you have a monitoring system and see that, in fact, that's the case. And so you get lots of different behaviors from this kind of a scenario. You get this fighting behavior where they sort of, one's trying to overcome the other. And when they fight, you can have some of them drive others off. So you can have one of them that cools. Its cold air gets sensed by another one's temperature sensor, and it causes that one to shut off. And it stays off until the data center gets so hot that that cold air itself actually heats up enough to bring the other one on. Others get stuck at 100% because when some get stuck off, there's not enough capacity remaining to regulate the temperature. And then often, they just oscillate furiously. They just thrash and wear out the equipment like mad, and the operators are left wondering why. Compressors that are supposed to last for 15 years are wearing out every year. So we've done this kind of stability analysis at other data centers, and we find qualitatively the same thing. This return air control strategy does not work. It's fundamentally flawed, and even more amazing is that we've done audits of hundreds of data centers, and I would say that I could count on my fingers the number of data centers that don't have this return air control strategy. So what this means is that all the telecom data centers that are supporting your mobile phone or whatever, all of the financial data centers that are supporting the banks, all the government data centers that are supporting all the processes of the government, all the data centers that support the internet, all of that stuff is susceptible to this vulnerability. And yet, there's, as far as I can tell, been no research on this. I find that really remarkable, and I think it'd be actually a great opportunity for some folks at Cal, maybe a graduate student, to take a look at this and see what could be done. So the need here, as I see it, is smarter controls. So you need to have controls that can take advantage of that multivariate analysis that goes into something as simple as calculating a relative gain array. I think that there's a lot of benefit to having a system that's predictive. So if you have this multivariable capability, you have a transfer function, you have the analytics built into it to calculate and figure out whether or not it's unstable, you can use it for predictive purposes. This one, I haven't touched on the need for this quite as much, but the fact is that in a data center, the IT equipment, the servers, all of that stuff, has an equipment life of about 3 years, but the cooling equipment has a life of about 15 years. So that means 5 equipment refreshes on the IT side for every 1 equipment refresh on the cooling side. So that means that stuff is just constantly coming and going. The racks come and go. The amount of heat they generate, the way that they're operated, the way that their internal controls work, all that stuff changes fully 5 times in the life of the cooling equipment. So to not have to go recommission data centers continuously, you have to have software that can essentially reconfigure and recommission itself. And then it has to be simple for operators and installers. You know, it has to be easy for them to use. It has to allow them to get access to the information. They have to be able to understand what it's doing and why it's doing it. And particularly during the installation phase, you know, this has to be installed if it's a retrofit in a live production data center. So anything that you do that's construction related in a live production data center is extremely risky. So you want it to be quick, non-disruptive, and you want to minimize the need for people to be having to make any kind of decision, because, you know, in every kind of mission critical environment, whether it's data centers or, you know, aircraft flying across the country, it's always human error that causes stuff to fail. You know, overwhelmingly, that's what goes wrong. The #1 cause of outages in data centers is somebody inadvertently hitting the emergency power off switch, which is there for safety purposes if somebody's getting electrocuted. There's a great big red button on the wall, and if you hit that, all the power gets cut. Well, guess what? It gets hit from time to time. And you know, I've heard people refer to that as the career-changing button. Yeah, and so you really want to, you know, minimize the amount of you know, need for humans to do things particularly during the installation phase of a system like this. So let me show you what we do. So we have a system that has some of these features. So the software itself is predictive. So what we have, well, it's a transfer function for those of you who know what that is, but we refer to it as an influence model. And what it tells you in this case is the influence of this air conditioner on all the sensors. So in this case, we had about almost 50 temperature sensors on this 10,000 square foot floor. And it's telling you the blue means that this one will cool these spots on the floor. So these 3 server clusters. And you can see actually a little pink right here. What it's predicting is that when this one gets activated on, supposedly to cool, it will actually heat up some parts of the data center a little bit. And we see that all the time. You know, air basically follows the path of least resistance. And if you turn this on, while you may pressurize areas that are near this unit, you know, you can just as well depressurize other places, and the amount of air coming out of the floor could go down. The flow pattern could change. You could get air sneaking from the hot aisle into the cold aisle. And so it's very hard to predict that ahead of time, but it's very repeatable. You know, you turn this on or off, and you can see that more or less the same thing happens over and over. Same thing for this one, and you can see just a very different pattern of behavior here. So like this one air conditioner that was up here, #3 also affects this server cluster. But it has a big influence in this higher density area in the lower right. Now, this demonstrates its ability to learn here. So what happened in this data center is that the customer, about 6 weeks after we put this in, they went and put in containment in this high density part of the data center, so that the hot air that gets discharged from these servers gets captured in that hot aisle, routed up over the ceiling, and back down into 4 of the 12 air conditioners on this floor. And you know, so that the idea there is to not mix hot and cold air for efficiency purposes, and that in fact did work. Air conditioner #3 was one of those 4 units, and you can see it just, you know, you can imagine if you put in containment like that, it has a huge effect on the airflow pattern in the data center. The software just automatically relearned by itself that this isn't the influence anymore. This is it now. It's almost entirely for this air conditioner in this now contained higher density area. And this is kind of interesting because what it exposes is that this predictive capability can reveal things about redundancy. You know, this server cluster between these 2 units used to have redundant cooling, and now it doesn't. You know, there's 10 other units on this floor, so it's probably not a problem, but you know, it reveals the other kind of things that you can do with a predictive system. The way that we deploy the whole system is illustrated by this diagram here. So we put sensors, little modules on the top of racks that have probes that measure rack top and bottom temperatures. These are usually wireless sensors. They get routed through a wireless gateway that has an IP uplink that software can get access to. And we can do this bidirectionally. So we can get sensor data, and then we can send commands out so that we can do control over the air, which allows us, again, to have a very quick, clean, simple installation of even the control actuations, which is really important in a mission-critical environment. We can instrument these kind of things because it's wireless in about 30 minutes. If you have a BMS and you need to integrate with it, that's done by open protocols that our system supports. And if you have those already networked together so that they had been, say, networked to the air conditioners, then we can use that path instead of this path. So what that looks like, is this here. So you can see the modules up here. You can see these probes coming down in front. This is a photo of what the wireless gateway looks like. So the effects of this, of having this system that allows us to rapidly deploy many sensors, gives us a lot, and our customers, a lot of visibility about what's going on in their data center. They're not left with having 1, 2, 5 temperature monitoring points that they alarm on. Now they can have hundreds of temperature sensors all over the place, put in just the right place so that they're measuring the temperature of the cooling fluid for the servers, which is the air temperature being drawn in at the front of those racks. The first thing the software does is stabilize those unstable local controls. It dynamically right-sizes all that capacity, figures out what should be on, what should be off, what should be turned up or down in a gross way, and then it optimizes the distribution. So maybe you don't need so much cooling over there and you need more over here. It figures that out and it optimizes it in a way that uses the least amount of power. So here's some examples coming up next that show you the impact of doing this. So this is a data center in Japan, as you can tell. You don't really need to be able to read any of this text. I'll just tell you what the graphs are showing us. So this one, and this one are showing us the compressor speed in hertz as a function of time over a number of days before and after the system was turned on, the system software. So here you can see just the mass amount of compressor thrashing on and off. They're going all the way from completely off up to their minimum, thrashing around between the minimum and the maximum, and a similar kind of thing over here. Lots of thrashing, a little bit less here. This one's obviously not completely shutting off. And then after the software comes on, you can see that it shuts this one off completely. It brings this one up to a high level and leaves it there. This one, it kind of corrects over a few days and then finally settles out to a fairly stable level. And this shows you temperatures on one of the racks, both before and after. So huge temperature swings, high-frequency temperature swings that are really destructive for IT equipment. All of the mechanical components inside a server are really adversely affected by the expansion and contraction of temperature cycles like this. Afterwards, nice and steady. And what this allows us to do is raise the temperature, and yet the peak temperatures don't go any higher than the peak temperatures that they had before. So we're able to get savings not only from just stopping all of this thrashing that occurs. There's a ton of energy wasted by all these starts and stops and cycles and everything else. But also we can raise the average temperature of the data center considerably, increasing the efficiency of the equipment and reducing the losses to the rest of the facility. And so here's an energy benefit. This is back to that state data center I was showing you. This is not the Japanese data center, but it's before. So this is just power for moving air around the data center. This is before. These little swizzles here are some tests that were being done on the system. Turn the software on, and in a matter of hours, it's down to less than half of what it was before, and it stays there for ever on. And so huge energy benefit, but wear and tear is a really big deal. And like I mentioned, it causes maintenance costs to be higher, and it causes failures. Sometimes failures that really matter, even if it's only a single piece of equipment. So this is yet a different data center where they have compressorized cooling in the air conditioners in North America, where instead of variable speed, they have 2 compressors and they stage them. So when it gets a little too hot, one of them comes on. Gets even more too hot, the second one comes on. Sometimes there are intermediate stages where they have different mechanisms for having a kind of half capacity of one air conditioner within the unit. And what this is showing in this particular data center is across the entire room, the number of compressor cycles per day. So this is the baseline period, and this is after the system's turned on. And you can see, after a number of days, it's figured out how to cut the number of compressor cycles to 40% of what it was before. So what causes compressors to fail by cycling? Well, first of all, they're sitting on spring suspensions that are intended to reduce vibration, and the springs fatigue. Every one of these compressor cycles is a jolt to those springs. And so after enough cycles, they break. And it's not like you can just replace the springs. You got to go in and replace the entire compressor because they're integral to the compressor. The windings in the electric motors that drive these compressors also get a shock, a mechanical shock every time you turn one of these things on or off. You know, when you turn it on, you get a surge of current, and that causes stress on the windings. And so what happens after a while, you get a little bit of mechanical friction. So every cycle is just doing a little bit of wear, a little bit of wear. Sooner or later, the windings get a short circuit and they fail. And it doesn't, you know, it doesn't matter whether it's slow or fast. I mean, just basically the speed just, you know, means, you know, if it's designed for 200,000 cycles on average, then on average, if you're cycling at 5,000 a day, you're going to be 2.5 times faster to failure than if you're at 2,000. But that's not the end of the story. If you cycle a lot, if you cycle enough, you end up with what's called short cycling. Short cycling has two problems. One is that if you short cycle a lot, you can have a situation where you end up sucking liquid refrigerant into the compressor. Most compressors aren't able to withstand that, and it will cause catastrophic failure of the compressor. The other thing that happens is the oil that lubricates the compressor is carried around by the refrigerant. So if you short cycle the compressor, the refrigerant doesn't reach a stable equilibrium case where it allows the oil to move completely around the compressor and lubricate the compressor. So the short cycles effectively cause the compressor to be operated without lubrication. And that obviously wears out compressors a lot faster. And so if you had 200,000 hours on your cycles on your compressor, if you cycle them very fast, you don't get 2,000. You get 100,000 or 50,000. And you're doing it faster, so it ends up failing. Instead of, say, 15 years, you end up failing in a year. So, you know, benefits of being able to solve these stability problems, a big reduction in energy consumption. We kind of typically see that, you know, if you have one of these data centers that's like over capacity, really thrashing around a lot, we can get about a 40% reduction, you know, even in these ones where they have hyper-efficient air conditioning. And that's because of the system effect. You know, when equipment manufacturers design the cooling equipment, they design it to be optimal like in a test room, right? They set it up for like what simulates a hot summer day, and they run it and they see what the COP is, and they say, oh, look at that, that's twice as good as anybody else's, and so it's a super efficient system. But if it's out there thrashing around, sometimes surging, and all those things that I just showed you, that just completely can erode the efficiency that you get from that. And so that system effect can allow us to get a 40% savings. We can get improved stability from less cycling, less on-off cycling, less up and down. That extends equipment life, reduces maintenance, makes the operation and maintenance guy's job a lot easier. But it also mitigates the risk of failure. So I mentioned before that one of the ways that, you know, instability can manifest itself is you get one air conditioner produces cold air that shuts off another one. And if it shuts it off in a way that's very powerful, the data center temperature might have to go up 10, 15, 20 degrees before it's hot enough at the discharge of the one that's on to allow the one that's off to get turned on. And so by mitigating that risk and having a system that provides sensors in the right place so that they can actually see what's going on in their data center with enough fidelity to be able to recognize problems, operators get to sleep at night. And that's a real big value because these guys like literally live in fear. And so just to summarize, you know, we talked about this instability, and what I assert is that, you know, this instability, particularly this problem with return air control, is a vulnerability for basically the entire internet. All of the infrastructure. Every time you go to any website, there's this kind of cooling equipment in the background allowing that site to work, and all of it is unstable. And that instability wastes energy, reduces the equipment life, and increases the risk that you're not going to be able to get those YouTube videos that you want when you want them. And solutions exist. So, you know, I talked about one that we have, but there are others out there, and there are other ways of solving this problem. And, you know, I think that it's a big problem, and it merits a lot of consideration.
Great. Thank you, Cliff. Let's open the floor for some questions. I'll start with you, Lindsay.
Thanks for an interesting talk.
You're welcome.
One of the questions that I have is, how were you able to start doing pilot projects of your technologies when these are such mission-critical facilities? Like, how did you convince them, and how did you sort of do small-scale and then eventually larger-scale pilot projects?
Yeah, good question. So there's sort of a few components to that. First of all, we didn't start off in mission-critical. We started off with an application for buildings like this one, and we got a system built that we could show, it worked, delivered the energy savings. All of the sort of nuts and bolts were the same. Some of the application software was a little different. So we had some case studies, granted not case studies in mission critical, but some case studies that could help customers get comfortable. We partnered with bigger organizations who, for various reasons, had a need for a system like ours, and we worked with them to go to their customers to line their customers up and help them help us convince those customers that this was the right thing to do. And then finally what we did is we took advantage of rebates in California to essentially deliver some of the first systems for no cost to the customer. So all of you who pay electricity in California essentially paid for us to get some of those first sites going.
I have a question. What happens if there is a bona fide power outage? I mean, do most of these data centers have backup generators? Or do some of the more critical aspects of infrastructure in this country, like finance or aeronautics, have duplicate data centers in different parts of the country?
Good question. It depends, but I would say that the ones that are the most critical have some combination of all of that. So in a, say, tier 3 or higher data center, they'll have a UPS, so they're not just running the IT equipment itself on utility power. And the UPS usually has the ability to keep the IT equipment running for 10 to 30 minutes before the batteries in the UPS run out. They'll have backup generators and they'll usually have the cooling equipment on the backup generators. The backup generators take anywhere from about 3 to 6 minutes to start. So if they have 10 to 30 minutes of backup power for the IT equipment, presumably they have enough time to get the backup generators started, the cooling back online, and keep the system going even in the event of a utility loss of power. Now, some of them do have backup data centers. So they'll have, if they lose, if they have a problem in one data center, they can actually just move all their operations over to another one. But that's really expensive. The other thing that happens is that some of the big monolithic apps like Google have, the whole app is distributed. So they can have actually a data center fail completely, and you might not even notice it because of the way that their app is designed. It's completely parallelized. And so if you try to get some information from Google and the first place it wanted to go isn't available, it can just go to another place. But most like financial services apps and things like that are not like that. And so if they need that extra level, they need to have that backup data center where they can immediately switch over. Yeah.
Hi, great talk. And yeah, data centers, this really is a huge problem, and especially like the analysis you did with the stability. I guess my question was, I would imagine this is a hot area that a lot of people are looking into, and as you mentioned, there are other solutions. So if you could give a quick rundown on how your solution might compare or differ from some of the other efforts that are out there.
So other ways that people are addressing at least certainly the energy aspects of energy problems in data centers are sometimes with monitoring systems that might have some analytics built into them that can provide recommendations on what to do. So they provide you not only with a data dump, but maybe recommendations like, we can tell that the efficiency of these units over here is starting to drop off, and you should go do something about it. Lots of sort of more efficiency by design. So going in and just simply retrofitting and providing more efficient operation through more efficient equipment that goes into the data center. I think there's quite a bit less on sort of the stabilizing the data center, because like I said, there's sort of this there's kind of this non-technical understanding among the sort of consulting engineering community in this kind of data center infrastructure space. But there hasn't been like a really clear technical analysis of what the problem is and ways to fix it. So that area, I think, is not really being addressed at all, as far as I can tell.
So in your model, it seems to me that you're basically using temperature to calibrate and test your model. Are there other variables like airflow and pressure that would also be helpful if you added those to both your physical measurements and to your model?
Yeah, good question. The usual things that people care about on the kind of power and cooling side of the data center are temperatures, number one, humidity, sometimes pressure measurement at various places, maybe the underfloor pressure or pressure drops across filters to see if they're loading up, things like that, and power. And we do all those things. We monitor all those things. The primary thing that we focus on controlling is temperature, because that's the thing that causes, for the most part, that's the thing, if it gets out of control, and it can get out of control quickly, will cause outages.
Hi. So you said you claim 40% energy savings. That was because the previous system is like constant airflow. But what if the previous systems already have variable speed drivers, and how much energy would be able to save after that?
Yeah, good question. So, I showed you some examples of like that Japanese example. That was in a data center where they have those all variable speed Japanese air conditioners. So they have variable speed compressors, variable speed evaporator fans, variable speed condenser fans. The whole thing is variable speed. It's twice as efficient as an air conditioner of the same sort that you'd find here in the US. And yet we've been able to get those same percentage numbers because of the system effect. Now, if the whole system is already more efficient because the cycle efficiency is better, the absolute kilowatt hours that you save might not be the same, but percentage-wise, the savings ability is still very high, and it's still in that range.
Getting my exercise.
Hey, Cliff, it's
Yes.
Nice to see your good work and huge savings.
Thank you.
Yeah. So my question maybe it's not a question to many of you, but it's to me. You mentioned a few times when the temperature is raised, then the efficiency really raised.
Mm-hmm.
So I would like to know the knowledge about this, because we are doing the office, office building, we are doing the same thing. If the equipment you are doing a huge capacity or the capacity of the chillers are not sized right, this happens often.
Yeah.
So why the temperature, when the temperature raised, then the efficiency is better, is higher?
Mm-hmm. So let me explain it in terms of air conditioners that have compressorized cooling. So you got the compressor, you have an evaporator where the heat's going into the evaporator's cold, and you got the condenser where the heat's coming out of the condenser, say like up on the roof or outside the building or someplace like that. That's where you're rejecting the heat to the atmosphere. So if the data center is cold, the temperature of the evaporator is going to be lower. And what happens then is that the temperature difference between the evaporator and the condenser will be greater. Now, the temperature difference in these two heat exchangers is directly related to the pressure because you have two-phase flow. So if you have so you got this high temperature outside in the condenser, a lower temperature in the evaporator. If the data center is cold, both the temperature and pressure difference are higher. And that pressure difference is what the compressor has to work against in order to move the fluid around the cycle. So if you can raise that evaporator temperature by raising the temperature of the whole room, then the pressure difference that the compressor has to work against goes down. And it goes down in a nonlinear way where, if you can make a little bit of a difference, it can make a big difference. And that's the mechanism for getting the efficiency up on those air conditioners. Yep.
Is it possible, I know a lot of high-tech companies are using solar and fuel cell sources of energy. Is it possible to use those to energize the backup, or do those have to be somehow base-loaded so they can't theoretically be used for that? Or not theoretically, but economically be used for that?
Well, yeah, I mean, I know some of these high-tech companies like Google are using solar a lot at some of their facilities. But you know, these days, like a new data center, if you're building a new data center, sort of the low end of the power consumption of the data center is like 10 megawatts. So to have like on the roof or out in the parking lot of your data center enough solar to, you know, to deliver 10 megawatts is not possible given, you know, solar technology as it is today. So, you know, I don't know, maybe there's some opportunity to like help keep batteries charged or something like that, but I don't think that it's possible given the, you know, the size and load density of these facilities for solar power to power them completely.
Two-part question. One, for data centers, LBNL and EPRI and others have been working on DC to DC data centers because they're digital devices, and showing 10% energy savings and 10% cooling savings.
Yeah.
I'm wondering if you've seen any uptake in that in the marketplace or in designs.
So we see DC power in telecom facilities because they have had that forever.
Right, right. Since you mentioned both, that's where it lives.
Yeah, right. I don't know of any place where they've put that in, you know, like in a recent construction, and especially, you know, if it's not telco, where they're not really familiar with that. I don't know of anybody that's done that. Even the telco guys, for their, you know, they're sort of like non-telco data centers, you know, they're different than the stuff that's, you know, managing, you know, phone lines and stuff like that. Even they often are not using DC power because it costs more.
Okay, thank you. The second part is knowing your beginnings and building aspect of it, just wondering if you could comment on how you're seeing the market with data centers versus buildings, and with Vigilent, how that's playing out.
That's a good question. So, you know, like I said, we started with an application for buildings, and we still have that, and we still have customers interested in that who are paying for that. But that market is, you know, it's harder to build a growth company in that area, I think, because it's not as important. So, you know, when especially like, you know, if times get tough or budgets get tight, you know, you can ignore your admin building. You cannot invest in it, and it will be okay. But, you know, you cannot ignore your $300 million data center and expect things to be okay. So they have to continue investing in their mission-critical infrastructure, but they don't have to continue investing in their non-mission critical infrastructure. So I think, you know, eventually that market for us will probably be much bigger because there's just simply a lot more of it. But in terms of, you know, a nice to have versus a must have, the data centers are more of a must have, and the admin buildings are more of a nice to have.
I think you probably answered that at the beginning with the fans in meeting room in Japan versus their data center cooling.
Exactly, right.
Okay, I think that's all for the questions. Great talk, Cliff. Thank you very much.
Thank you.